My name is Phang and my matrix number is 202599. I am the leader and the video editor for Group 6. Our topic for Group 6 is Gauss law. What is Gauss law? Gauss law, also called Gauss-Flash theorem, means a law that is related to the distribution of electric charge and the resulting electric field. Besides, Gauss law states that the net electric flux to any hypothetical closed surface equal to 1 over vacuum permeability times the net electric charge in that closed surface.
Next.
Now, we will discuss about the history of Gauss law. The Gauss law were defined by Joseph Louis VIKNSH in 1773 years. In 1813 years, the Gauss law was further developed by Charles Friedrich Gauss. Gauss law is one of the various four equations which form the basis of classical electrodynamics, the branch of physics which deals with rapidly changing electric and magnetic fields. In years 1831, Gauss began to apply mathematical potential theory to the real world. Gauss became acquainted with Wilhelm Weber, a physics professor at the University of Göttingen. The two scientists shared an interest in electricity and magnetism and quickly developed a friendship. Their association led to a number of advances in this field. Soon after their meeting, Gauss and Weber began works relating to terrestrial magnetism and later discovered Kempfer's laws of electric circuit. In order to speed communication with one another, Gauss and Weber also constructed a telegraph system that linked Weber's laboratory to the observatory nearly a mile away. Gauss used his formidable mathematical ability to analyze the behavior of electric and magnetic fields. Using his divergence theorem, which he discovered independently of Joseph Louis VIKNSH, he formulated two laws in 1835 years. Gauss' law, which related an electric field to the distribution of electric charge that causes it. Gauss' law for magnetism, which states that magnetic monopoles do not exist. Written mathematically, this law forms two of the four equations needed to combine the electric and magnetic fields into a single unified electromagnetic field. The unification was achieved by James Charles Maxwell in 1864 years.
Next.
Let's say that we have an enclosed surface of sphere, and in that sphere we have Q, which is the enclosed charge. We put the value of the enclosed charge is equal to 0, and we applying the electric field line that into the surface of the sphere, and something goes inside must go to the outside. So there is also the electric field lines that going out from the surface area. But due to the Q is equal to 0, meaning that if no charge in the sphere, the lines cannot be terminated, so it will be giving the electric flux is equal to 0. Now we have another different sphere, which is we have a Q, also Q inside it, and this Q is value is positive or negative, and then we applying the electric field into the sphere and the outside of the sphere. We will get the answer is in quantitative because Gauss law give it in the quantitative answer. Okay, previously that I have said that there is the electric field line that are going into and outside of the sphere surface. And considering we take the electric field line that going outside of the spherical surface, we can see here in the picture that the electric field line from Q, it must pass through the surface area of radius 1 and radius 2. That will give the electric flux of radius 1 and radius 2 will get the closed charge is equal, and the value of the flux is independent on the size of the surface, which means the value of R1 and the electric flux of R1 and R2 will be differ, and the electric field line that are going to pass through these two surface it has the same direction as other, meaning that the electric field line 1 is same direction with the electric field line number 2. So we will get the net line which is equal to the number of line from the inside to the outside minus the number line from the outside to the inside. Based on the previous slide that is explaining on the behavior of the electric field lines with the enclosed charge, that proven the statement of the Gauss law, which is, according to the Gauss law, the flux of the electric field through any closed surface, which is another name is Gaussian surface, is equal to the net charge enclosed divided by the permittivity of free space. So we can see that here actually when the electric field lines that are going outside from the enclosed surface, the charge is positive, and when the electric field lines going into the enclosed surface, the charge is negative. So that's fine.
Assalamualaikum and hi. My name is NAJIHAHNOORDIN by matrix number 202464. I'm going to explain about Gauss law equation and its derivation. For the first slide, as we can see, this slide consists of 6 equations of Gauss law. The first equation is about the definition of electric flux for a uniform electric field. The second one is electric flux through an open surface. The third one is electric flux through a closed surface. Then we have a Gauss law equation, and next is Gauss law for system with symmetry equation, and lastly the magnitude of electric field just outside the surface of a conductor. Gauss law, which state that the electric field is equal to the charge divided by 4 pi epsilon naught multiplied by r squared, where r in this case is the distance. It's essentially the radius of our sphere. We begin by stating the electric field, so the net electric flux for this particular case equal to the closed integral of our dot product of our vector, electric field vector, and infinitely small area given by dA. Now, this is by definition of what electric flux is. For this particular case, our electric field is given by this ratio. We can replace electric field in figure electric field which is labeled as 1.59 and replace it with 1, which is the entire equation. Notice our Q is the constant. 4 pi epsilon naught are constant, and our R is a fixed quantity. We can take entire fraction and bring it outside of the integral. Then we will get the last equation. If we evaluate the ratio multiplied by the surface are given A, as we dealing with spherical surface, that means the surface area is simply 4 pi multiplied by r squared. So we can replace A with 4 pi multiplied by r squared. After we do the cancellation, we are left with electric flux in the particular case equal to the closed integral of EdA equals our Q inside region divided by epsilon naught. So that's how we got the final equation for the derivation.
Hi, my name is ZIYI. My mesh number is 201401. Okay, my friends in the previous lecture talked about some equations of Gauss law, and now I'll put some of them back here and review them briefly. So first of all, the basic Gauss law is the total of electric flux out of a closed surface is equals to the charge enclosed divided by the permittivity. And Gauss law in integral form is the area integral of the electric field over any closed surface is equal to the net charge enclosed in the surface divided by the permittivity of space. However, more commonly encountered is the inverse problem. Given the distribution of charges by the electric field at a given location, this is a more difficult problem to solve. Although the electric flux across a closed surface is known, this information is still not sufficient to solve the problem. The electric field at any location on a closed surface can be very complex. The problem itself shows some symmetry, such that the magnitude of the electric field at the location of the closed surface become uniform. This uniformity can be exploited to calculate the electric field. Symmetries in a space such as cylindrical symmetry, planar symmetry, and spherical symmetry, and so on can help Gauss law to solve the problem. And about this basic Gauss law, please notice that where E is the electric field and dA is vector representing in individual element of the area of the surface, and Q is the charge in the closed surface, and epsilon 0 is the vacuum permittivity. Okay, next, let's move on how the equation Gauss law applies. As we said before, basically there are only three types of symmetry that allow Gauss law to be used to deduce the electric fields. So they are a charge distribution with spherical symmetry, and a charge distribution with cylindrical symmetry, and also planar symmetry. Deploy of the symmetry, we perform the calculation in appropriate coordinate systems and use the right kind of Gaussian surface for that symmetry. So for solve this problem, we have to do 4 steps for solve the problem. So the 4 steps is charge distribution and consequences of symmetry, and the third one is Gaussian surface and flux calculation. Last one is use Gauss's law. And here is the application of Gauss law for these 3 types symmetry. So the first one, the formula is spherical symmetry, and the second one is cylindrical symmetry, and the last one is planar symmetry formula.
Next. Based on spherical symmetry, if the charge density is only a function of r that is not equal to rho bracket r, then you have spherical symmetry. If the density depends on theta or pi, you could change it by rotation. Hence, you will not have spherical symmetry. Now we'll discuss about consequences of symmetry of spherical symmetry. R is the unit vector pointed in the direction from the origin to the field point P. The radial component E rho of the electric field can be positive or negative. When E rho bigger than 0, the electric field at P points away from the origin. When E rho smaller than 0, the electric field at P points towards the origin. Based on the figures, we will know that charge density is constant in the cylinder. Second, upper half of the cylinder has a different charge density from the lower half. Third, left half of the cylinder has a different charge density from the right half. Fourth, charges are constant in different cylindrical rings, but the density does not depend on the polar angles. Cases A and D have cylindrical symmetry, versus B and C do not. Now we'll talk a little bit about planar symmetry. In the diagram, we will know that the charge distribution with planar symmetrics. Take the plane of the charge distribution to the xy plane, and we find the electric field at the space point P with coordinate x, y, z. Since the charge density is same at all xy coordinate in the z equal to 0 point by symmetry, the electric field at P cannot depend on the x or y coordinate of point P.
In this part of the video, we are about to go through on the importance and limitation of Gauss' law. Now, you might think, does a well-known law like Gauss' law has its limitation? Yes, it does. Let us have a look. But before we look into the limitations of Gauss' law, let us first have a look at the importance of Gauss' law, as it brings great significance in the daily application of science. Gauss' law can be very important as it helps in solving complex electrostatic problems by making calculations much more approachable. Besides that, there are some cases in which calculation of electric field is quite complex and involves difficult integration. Gauss' law simplifies the evaluation of electric field by giving us an option to skip integration. Therefore, Gauss' law is basically another way to find out electric field due to the charge distribution, but it avoids unnecessary integration, which is obviously one of the most difficult calculations. Despite having its benefits of making our calculations easier, Gauss' law is also said to have its limitation. One of the few limitations of Gauss' law is that it only can be used for special cases where the surface is symmetric around the point charge. For example, if we were to use a conical Gaussian surface, the Gaussian surface is said to be non-symmetrical around the point charge, and eventually this does not allow us to use Gauss' law in our calculation, which in turn only allow us to use the harder way of calculating the electric field. Next, Gauss' law can only be applied if the electric field is symmetric. For example, if the electric field is making an angle of 90 degrees at the surface vector, hence the electric field should make an angle of 90 degrees at each and every point of the surface vector or the Gaussian surface. Therefore, we can conclude that the electric field should be symmetric in respect to the surface vector. Lastly, Gauss' law requires the point charge to be at the center of the Gaussian surface at most cases, but however, Gauss' law allows the point charge to be at some other location at certain cases. However, the point charge can never be at the boundary of the Gaussian surface. This is because Gauss' law cannot be applied when the point charge is at the boundary of the Gaussian surface.
Metric number 204625, and my part is example question using Gauss law equation. So we look at here, an infinitely long cylindrical conductor has a radius of 30 cm and a surface charge density of 15 microcoulomb per meter square. So find A, total charge enclosed by Gaussian cylinder of radius 1.5 meter and length 2 meter. For part B, the electric flux that passes through the Gaussian cylinder. And now, this is figure for cylindrical conductor. The outside of that is layer cylindrical. This is going to be a Gaussian cylinder. So this is Gaussian cylinder. Now the positive charge here uniformly distributed throughout the cylindrical conductor, and that positive charge rests on the surface of that conductor. Capital R here is the radius of the cylinder, and the small r here as the radius of the Gaussian cylinder. The electric field is going to emanate away from the positive charge, and the length of the Gaussian cylinder here is L. L is length of Gaussian cylinder. So we go into part A. Part A here, focus on part A. What is the total charge enclosed by Gaussian cylinder? So we know that the surface charge density sigma is equal to Q over Q divided by A, which is A here is area. So the Q is sigma times A. So here A here not area of the circle on top, it is a lateral area. So surface area SA, surface area here equal to 2 pi r squared plus 2 pi rh. So this is going to be a Q equal to sigma times 2 pi r L. L here is length of Gaussian cylinder. So Q equal to 2 pi multiplied by 0.3. Why 0.3 here? Because we convert from centimeter to meter. So we got here 0.3 meter and multiply by 2 meter. And the final answer here we got 5.65 times 10 power of negative 5 coulomb. So the unit here is coulomb. So we're going to part B here. The part B, we can see the part B here is the electric flux that passes through the Gaussian cylinder. Gauss law states that the electric flux that passes through a Gaussian surface is equal to the total charge enclosed by the surface divided by epsilon naught. So here is Q divided by epsilon naught. We got the answer from A here. So we got 5.65 multiply time to 10 power of negative 5 coulomb divided by epsilon naught is 8285 times 10 to power of negative 12. So the final answer here is 6.38 times 10 to power of 6, and the unit here is Newton times meter square divided by coulomb.